A group of astronomers led by the Royal Observatory of Belgium and the KU Leuven has made a noteworthy discovery suggesting that high-frequency magnetic waves may be crucial in maintaining the Sun's atmosphere at incredibly high temperatures. This finding brings new insights into one of the most intriguing solar mysteries, the reason behind the Sun's outer atmosphere being hotter than its surface. The enigma of coronal heating has long puzzled astrophysicists. Typically, temperature decreases as you move away from a heat source, but this is not the case for the Sun. Despite its heat source being confined to its core, the corona, which is the outer layer of the solar atmosphere, is approximately 200 times hotter than the Sun's surface. Professor Tom van Dorselaer at KU Leuven explains, "Astrophysicists have been attempting to solve this puzzle for the past 80 years, and now there is increasing evidence that magnetic waves may be responsible for heating the corona." This new understanding comes from observations made by the Extreme Ultraviolet Imager Telescope on board the Solar Orbiter, a spacecraft operated by the European Space Agency, which is currently observing the Sun from a position behind it. The Extreme Ultraviolet Imager Telescope, managed by Royal Observatory of Belgium, provides highly detailed images of the solar corona, revealing rapid oscillations in the smallest magnetic structures of the corona. The energy carried by these high-frequency waves appears to contribute significantly to the heating of the solar atmosphere. The main question the scientists sought to answer was whether the energy generated by these new, fast oscillations outweighed the energy from similar but slower oscillations that were already known. To address this, the scientific team conducted a meta-analysis, which involves using multiple scientific studies to derive common insights. Dr. Dae Lim, the lead author, concluded that high-frequency waves play a more substantial role in the total heating of the corona compared to low-frequency waves. Dr. David Bergmans, the principal investigator of Extreme Ultraviolet Imager, comments, "Since her results point to the crucial role of fast oscillations in coronal heating, we will focus on detecting higher-frequency magnetic waves with Extreme Ultraviolet Imager." The Sun's corona has been a fascinating enigma for solar physicists due to its inexplicably high temperatures. While the Sun's visible surface, known as the photosphere, registers temperatures of about 5,000 degrees Celsius, the corona's temperatures soar into the millions of degrees Kelvin. This extreme temperature difference has puzzled scientists for nearly a century, and it is commonly referred to as the coronal heating problem. To address this long-standing mystery, the team of researchers turned their attention to the Sunspot Ombre, which are the darkest and coolest regions on the Sun's surface. Sunspots are areas with intense magnetic activity, and their umbrae represent the central darkest parts of these regions. The Sun's strong magnetic field inhibits the transfer of heat from the Sun's interior to the photosphere, resulting in the cooler temperatures observed in the umbrae. Using the advanced 1.6-meter Good Solar Telescope at the Big Bear Solar Observatory, the scientists were able to observe transverse oscillations in plasma fibrils within the sunspot umbrae. These fibrils are slender structures that appear like cone-shaped threads and are characterized by strong magnetic fields, measuring more than 6,000 times stronger than Earth's magnetic field. The groundbreaking discovery came when the team detected lateral oscillations in these dynamic fibrils, indicating the presence of fast waves within the sunspot umbrae. These fast waves play a crucial role in the transportation of energy. The waves travel upwards through vertically elongated magnetic channels, similar to magnetic conduits reaching the Sun's corona. As the waves propagate through the solar atmosphere, they contribute to the intense heating of the corona, ultimately maintaining its high temperature. The researchers employed numerical simulations to estimate the energy carried by these fast waves. The results revealed that the energy transported could be thousands of times stronger than the energy losses occurring in the active region plasma of the Sun's upper atmosphere. In fact, the dissipation of energy by these waves is estimated to be up to 4 orders of magnitude greater than what is required to sustain the scorching temperatures observed in the corona. This groundbreaking finding not only sheds light on the sunspot umbrae, previously regarded as simple and static regions, but it also provides crucial insights into the processes responsible for heating the solar corona. Nonetheless, despite this significant progress, the researchers emphasize that the coronal heating problem is not entirely resolved. While the discovered fast waves appear to be responsible for heating the corona above sunspots, there are still unexplained phenomena. There are regions in the Sun's corona known as hot coronal loops, which lack sunspots but exhibit high temperatures. These regions pose a separate puzzle yet to be fully unraveled. The researchers express confidence that the high-resolution observational capabilities of Good Solar Telescope and Big Bear Solar Observatory will continue to provide valuable data, allowing scientists to delve deeper into the complexities of the Sun's atmosphere and potentially unlock more secrets about the mechanisms behind coronal heating and energy transport processes. In conclusion, this study marks a significant advancement in our understanding of the Sun's corona and the perplexing coronal heating problem. By exploring the dynamic fibrils and fast waves originating from Sunspot Ombre, researchers have found an essential piece of the puzzle. Nevertheless, the quest for a complete understanding of the Sun's complex behavior and the processes governing its atmosphere continues, offering exciting opportunities for further research and exploration.